Okay, part 2, performing the row operation. So we're going to take this matrix, and let's first do this row operation that's described here. Take -3 times row 1. I'm going to add that to row 2. Let's try this again. -3 times row 1. Add that to row 2. That's going to become our new row 2. So row 2, it says this is going to equal row 2. So row 2, the middle row, is the row that's going to be affected. These are the entries of row 2 are the ones that are going to change. So each entry, we have to take -3 times row 1. That's going to change this 1 here to -3. So this is -3 added to -1. Makes that a -4. Here, -3 times -4 is 12. 12 plus -6 is 6. -3 times row 1 here changes to -9. -9 plus -6 is -15. And here, -3 times -7 is 21. 21 plus 8 is 29. Now, the second row operation here is we're going to take 2 times row 1, add that to row 3. That's going to become our new row 3. So now row 3 is being affected. We have to take 2 times row 1, so this is 2 times 1, which is 2, add -7, we get -5. 2 times row 1 makes -8, added to -5 makes -13. 2 times row 1 is 6. 6 plus 6 is 12. 2 times row 1 here is -14. -14 plus 8 is -6. Row 1 remains unchanged. Okay, number 7. We can only add matrices if they have equal dimensions. So this matrix right here is a 2 by 3. There's 2 rows, 3 columns. Matrix B is also a 2 by 3. So the dimensions are exactly the same. To add matrices, we add entries that are in corresponding positions of the 2 matrices. So 10 and this -7 are in corresponding entries or in corresponding positions. 10 plus -7 is 3. 0 and -5. -5, 4 and -7. -3. -2 plus 7 is 5. -5 plus -9 is -14. And 4 plus 8 is 12. Okay. Multiplying 2 matrices. First we need to check the dimensions of the matrix A and matrix B. So matrix A is a 2 by 3. Matrix B has 3 rows and 2 columns. These inside numbers have to match in order to make the multiplication possible. So the multiplication is possible. The outside numbers here tell us that the answer, when A is multiplied by B, that's going to result in a 2 by 2 matrix, a square matrix. So here's matrix A. In matrix B, I'm going to write up here. And A times B is going to result in a 2 by 2 matrix here. The entry that goes right here is in the first row, first column. So we're going to go across that first row, down the first column here. So 3 times negative 1 is negative 3. We're going to add that to, I better make this matrix a little bit larger so I can fit it in. Okay, 3 times negative 1 is negative 3. We're going to add that. Negative 8 times 8 is negative 64, and then negative 5 times negative 7 is positive 35. This entry right here, this is the second row, but it's still the first column. So we need the second row, still the first column. 6 times negative 1 is negative 6. We're going to add that. 6 times 8 is 48. 7 times negative 7 is negative 49. Okay. This entry right here in this spot, this is the first row, but second column. First row, second column. Now, 3 times 10 is 30. Negative 8 times 3 is negative 24. 5 times 7 is negative 35. Now this last entry here, this is the second row, second column. So second row down here, first column over there. 6 times 10 is 60. 6 times 3 is 18. 7 times 7 is 49. No, just simplify. Negative 3 times negative 64 is negative 67. Added that to 35 and you get negative 32. Over here, 30 plus negative 24 plus negative 35. Negative 29. So in here we have negative 6 plus 48 minus 49, that's negative 7. 60 plus 49 plus 18 is 127. The inverse of a 2 by 2. You need to remember this. So A times D is 6, and we're subtracting B times C, that's negative 1. And then D and A switch places, B and C switch signs. And I'm okay on a problem like this if you leave the 1/7 out of the matrix. 1/7 is a scalar. If you did multiply the scalar into the matrix, that's fine too. You'd get negative 2/7 here. You'd get positive 1/7. Here you get negative 1/7. And in this entry you get negative 3/7. Okay. Matrix algebra. Now read the directions. It says solve the system using matrix algebra. If you solve the system any other way, then by clearly showing matrix algebra, then you won't be getting credit for this problem. Okay? It's fine if you solve it another way just to check your answers, but I have to see matrix algebra. First thing you need then is a matrix equation. A matrix equation is a coefficient matrix. So this is a matrix containing the coefficients. We have a matrix containing the variables and a matrix containing the constant negative 1 and 12. So if we imagine this as matrix A, we can call this X and call this B. What we need to get is X. We want to get X by itself. Right now it's being multiplied by matrix A, so if we apply the inverse of A, that would result in not canceling a matrix A, but multiplying a matrix by its inverse produces the identity matrix, which is just 1 essentially. But if we multiply by the inverse on the left, we have to multiply by the inverse here on the right side. So what we need to find solution-wise is we need to find A inverse and times that by our matrix B. Now this was done on purpose. If you notice this matrix here, matrix A, it's the same as matrix A in the problem above it. And they're exactly the same. We've already found the inverse for matrix A. It's right here. A inverse what we're supposed to do is multiply the inverse of A times B. So I'm going to write matrix B here. Matrix A is a 2 by 2. Matrix B is a 2 by 1. So the inside numbers here match. The outside numbers 2 and 1 tell us that our solution is going to be a 2 by 1 matrix. Now I'm going to perform the multiplication on the matrices first, and then I'm going to times the 1/7 into this matrix here. So negative 2 times negative 1 is 1. That's going, or sorry, negative 2 times negative 1 is 2. That's going to be added to 1 times 12, which is 12. 2 plus 12 is 14. And here negative 1 times negative 1 is 1. Negative 3 times 12 is negative 36. 1 plus negative 36 is negative 35. Okay, and then when I times that by 1/7, that's going to produce a matrix of 2 comma, or 2 and then negative 5. So the solution is x equals 2, y equals negative 5. The solution to a system of equations, remember though, is an ordered pair, 2 comma, negative 5. Okay, the determinant of a 2 by 2 matrix. So if we consider this to be matrix A, then the determinant of A, which is denoted by these two upright vertical bars, is A times D subtract B times C. So it's going to be 5 times 5, which is 25. We're going to be subtracting negative 21, which is 46. Okay. So a 3 by 3 determinant. In class I did show 2 different ways to find the determinant of a 3 by 3 matrix. I notice here that there's a 0 along this first row. So I'm going to expand along this first row, finding the cofactors and the minors. So if I take 8 right here as my first cofactor, cross out the row and the column that contain that cofactor, that's going to leave this minor right here, the determinant 1, 3, 5, 9. Now, if you remember, there was a pattern I showed you for a 3 by 3. It's plus, minus, plus, minus, plus, minus, plus, minus, plus. Since we're expanding along the first row there, we need to follow this pattern. So the next cofactor we have to subtract, and it's negative 1. So if I cross out, so this is a cofactor, if I cross out the row and the column containing it, that leaves this minor here, the determinant 3, 8, 3, 9. Okay, now I take this cofactor 0, cross out the row and the column containing that cofactor, that leaves this minor 3, 1, 8, 5. Now the determinant of this 2 by 2 matrix is 9 minus 15. The determinant here is 27 minus 24, and then 0 times anything is going to result in 0, so those we don't need to worry about. This turns into 8 times negative 6 plus 1 times 3. This is negative 48 plus 3, which is negative 45. Now that was the first way I showed in class. The other way, I'm going to erase all of this. Now I chose to expand along that first row. That method would work if you expanded down the column or anywhere actually, but I noticed a 0 here. Now the other way, you had to take this column and rewrite it here, 8, 3, 8, and then this middle column, negative 1, 1, and 5. So what we're going to end up with is a big parenthesis here. We have to subtract another parenthesis. All the entries in this parenthesis come from making products along these diagonals here, this one, and this one here. So along this diagonal I have in blue, 8 times 1 times 9 is 72. I'm going to add that. Negative 1 times 3 times 8 is negative 24. And then this diagonal is going to produce a 0. So it's very important that this is in the right order because subtraction is not commutative. Okay, going from top down, from left to right, all of these products go in this first parenthesis here. Now in this parenthesis that we're subtracting, we need to form products going the other way. This way, and this way. So this first product is going to be a 0. We're going to add the next product, which is 5 times 3, which is 15, and then 15 times 8, which is 100, looks like it's 130. And then this product here, 9 times 3, and that's a negative 1. 9 times 3 is 27 times negative 1 is negative 27. So what we have here is 72 minus 24. That's 48, and we're subtracting 130 minus 27 is 103. And then 48 minus 103, let's see if we have 103. Take away 48. It's going to be negative 45. So you get the same answer either way, just a different method there. Actually, let's see. You know what? This should be 120. Yeah. I was going to say this is not adding up. Okay. 120 minus 27 is 93. Okay, there we go. That's working out. Now we get negative 45. Okay, question 13, a matrix. So this is already a matrix equation. What they're wanting is the system of equations that we can form from this matrix equation. We don't have to solve for x, y, and z on this problem. A matrix equation, if you understand where it's from, this is the coefficient matrix. So these numbers here represent coefficients of variables, and these are the three variables, x, y, and z. So it's going to be 1x or just x here, and then this is a coefficient of y plus 4y minus 3z is equal to negative 21. Negative 5x minus 3y plus z is equal to 20. And 8x plus y plus 5z is equal to negative 13. Cramer's rule involves finding determinants. Okay, there's three determinants we need to find: determinant d, determinant d sub x, and determinant d sub y, because there's an x and a y. And then Cramer's rule says that the solutions then for x is d sub x divided by d, and y is d sub y divided by d. Now the determinant just d is the determinant of the matrix formed by the coefficients there. So this is negative 3, 1, negative 1, and negative 2. The determinant is AD, so this negative 3 times negative 2, which is 6, minus negative 1, which is 7. Now the determinant d sub x, the subscript here is important because this subscript tells us which column needs to be replaced in this D matrix. The x column will be replaced with the constants negative 1 and 12. So the new matrix, in place of the x column, we're going to have negative 1 and 12, and we're still going to have negative 1 and negative 2 in the y column. This determinant is going to be 2 minus negative 12, which is 14. Now d sub y, the subscript here, y, tells us that the y column is going to be replaced. So if we go back to the original D matrix here, the y column, negative 1, negative 2, is replaced with our constants negative 1 and 12. So negative 1 and 12. The x column stays the same as the original matrix. Negative 3 times 12 is negative 36, and we're subtracting negative 1, which is negative 35. So here, d sub x is 14 over 7, that equals 2. That tells us that x equals 2. Here, d sub y is negative 35. Divide that by 7, we get negative 5. So our solution is 2 comma negative 5. And if you remember, this system of equations showed up a little while ago in one of the other ones that is also done on purpose, just so you can make sure that you get the same answer both times. That's just a way of helping you there. Okay. Solve the system using an augmented matrix and reducing the augmented matrix to row echelon form. Another way of saying this is Gaussian elimination. So the first thing we need is our augmented matrix. There's going to be 1, negative 2, 1, and 1, 0, 1, 2, 5, 1, 1, 3, 8. So we already have a 1 in the leading spot, in the leading entry of row 1, and there's also a 0 beneath that. So our first task should now be to look at this leading entry. This should be a 0 right here. Okay. So if we made row 1 negative 1 and added that to row 3, that's going to produce a 0 right there. So our first row operation could be negative 1 times row 1, add that to row 3, and make that our row 3. So that's going to be 0 there. Negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 2 is 2. 2 plus 1 is 3. Negative 1 times 1 is negative 1 plus 3 is 2. And then negative 1 times 1 is negative 1 plus 8 is 7. So now we have a leading entry of 1 on the top row and zeros beneath it. Once that's accomplished, the next task is to go to the middle row of the leading entry. This should always be a 1. It already is in this case. If it weren't, we'd have to multiply this whole entire row by the reciprocal of whatever that number is. But we have a 1 here already, which means our next task should be to get a 0 beneath that. So what can I add to 3 to make it 0? Well, it has to be negative 3. So I'm going to take row 2 and multiply it by negative 3. That's our next row operation. Negative 3 times row 2. Add that to row 3. That's going to be our row 3. So row 3 is still a 0 there. Now negative 3 times 1 is negative 3, plus that 3 makes a 0 here. Negative 3 times 2 is negative 6, plus 2 is negative 4. Then negative 3 times 5 is negative 15, plus 7 is negative 8. And we're almost there. This bottom row now needs to have a leading entry of 1. That's what row echelon form means. All the leading entries have to be a 1. So if I take row 3 and multiply it by negative 1/4 and make that our new row 3, that's going to give us a row of 0, 0, 1, and 2. 0, 1, 2, 5, then 1, negative 2, 1, 1. Now if we take a look at what this augmented matrix represents, this augmented matrix still represents a system of equations. It's just been simplified. The bottom row represents the equation z equals 2. The middle row of the matrix represents the equation y plus 2z is equal to 5. And the top row represents the equation x minus 2y plus z is equal to 1. So starting at the bottom and backwards substituting up through this system of equations at z equals 2, then this z equals 2, so this middle equation becomes y plus 4 is equal to 5, which means that y is equal to 1. Now using our values for z and y, this top equation becomes x minus 2 times 1, which is minus 2, plus z, which is another plus 2, which equals 1. Therefore x is equal to 1. So our solution is x equals 1, y equals 1, and z equals 2. Okay, I'm going to stop this one and make a new part 3, which will cover all of the story problems.